Everyone. I'm Anupam Mitra. I'm a new postdoc here at Berkeley Lab. And thank you, Armal, for the introduction. And thank you for organizing this event. Grateful for the opportunity to share some of the results I did as a PhD student at the University of New Mexico, as a part of a program funded by the Quantum Systems Accelerator led here out of Berkeley Lab. So my talk will be about microstates and macrostates in classical simulation of 1D Ising models. Now, the main thing is, and in quench dynamics particularly, the main thing is I'll talk about classical simulation, no quantum data here. But if this title seems too wordy for you, you could just think that my talk is about when do we need quantum computers and when we don't. Right. So, we know that quantum states live in an exponentially large space. That's why we get our salaries to figure out what we can do with that. And there's this belief that quantum simulation might be an easier problem. So let's say this circle here represents the entire exponentially large Hilbert space. And these are some quantum states I've picked over here. And let's say because of noisy devices or other issues I have, I can only access some of these black circles, and the others are not accessible to me. Now, what we expect is if I'm trying to calculate quantities of interest for many-body physics, I may not necessarily need all of these states. And in particular, the quantum simulation problem may be more forgiving. And this is really because many of these states are consistent with the same macro property, which is what informs the problem of interest for many-body physics. So with this context, if I want to draw this phase diagram, then if I can get all the information I need from just these accessible quantum states, perhaps I can construct this phase diagram and study them. So in this context, I just want to bring up a quote from John Preskill, which really inspires a lot of work we do in analog quantum simulation, which is that what is the major challenge we have is what can we do with analog quantum devices that are actually hard to simulate classically, but also robust with respect to error that we can't clean up before we have fault tolerance. So in this context, what we'll talk about today is approximating macro properties in a quantum simulation using classical methods, and in particular, I'll focus on critical phenomenon 1D Ising models. Now, these are dynamics. So what I'll talk about is dynamics, but first, many of us brought this up, but I just want to remind everyone of matrix product state. So what a matrix product state does is takes a many-body wave function and factors it into a matrix product of higher order tensors, and the bond dimension quantifies the amount of entanglement in the state. So it lets us interpolate between a product state, which is area law entanglement, and highly entangled states where we have volume law entanglement. And we can think of this bond dimension as a tuning knob to see how much entanglement we need to calculate the things of interest to us. And these MPS time evolution algorithms scale polynomially in this bond dimension. And if they are not exponential, then things are efficient. So what I'll talk about for the next few minutes is a dynamical quantum phase transition in Ising models. Our Hamiltonian is a transverse field Ising model. We have interaction along the z-axis. Now, even though we are working in 1D, we do have long-range interactions characterized by a power law, and we also have a transverse field. So for this Hamiltonian, we do have a pi rotation symmetry. And for the purpose of this phase transition, we will prepare an initially symmetry broken state, which obviously breaks this pi rotation symmetry. And then we'll quench it to this Hamiltonian and ask the question, if I define these order parameters, which are, for example, the single spin expectation value, also known as magnetization, or two spin correlation. And if I do some space-time averaging of this, as you can see, this is where the macroscopic aspect of the problem comes in. Then if I also do the standard ideas of phase transitions, I take the thermodynamic limit where the system size goes to infinity. But because this is a dynamical thing, we also need to take the equivalent limit in the time direction, which is the steady state limit, which is that my quench is long enough. Then the initial broken symmetry would either stay broken or get restored. I can see that in the other order parameter as well, where we have a negative slope or a positive slope with respect to the quench transverse field. And what we'll really study is this phase transition in between. Okay, so now this is of interest in analog systems. In particular, I want to highlight this experiment from a few years ago where this exact phase transition was probed in a 53-qubit trapped ion simulator using analog dynamics, and these exact order parameters were measured. And obviously, for small enough systems, you can do exact diagonalization, have a theory curve, and see that everything falls along with the theory curve, so things are great. However, for 53 spins, the authors of this study pointed out that exact diagonalization is not possible, so they don't have theory to fit that. And the question which I have is, can we reproduce these order parameters without doing exact diagonalization with just low bond dimension matrix product states? And the answer is yes. That's why I'm here to tell you about it. So here is an example of what we did. So we took a 90 spin system and we did the same quench, and we do see this characteristic change in MZZ, the order parameter, as a function of the quench transverse field. Now this is for 90 spins, so obviously I can't do exact diagonalization. The Hilbert space dimension is huge. This number makes my head hurt, 10 to the 27. But we do see the qualitative features of the symmetry broken state phase with a negative slope, the symmetry restored phase, and we see the signature of the dynamical quantum phase transition. And notice that there are different curves here. They correspond to simulations done with the matrix product states, time evolved with different bond dimension. And we see that it doesn't change with different bond dimensions from 8 to 128. Now, these are tiny compared to what I would need to write down the full wave function, which is 2 to the 45, again, a very large number. So let's try to be a little quantitative and see where the transverse field, what the critical transverse field is by trying to figure out what the minima of this curve is. And if we do, please.
So you're evolving in time, but you're also doing a time average. At some point, you get the observable, right?
Yes.
So your bond dimension is growing as you go in time?
Yes, it is.
And then you're doing cuts to keep it within that range.
That's right. So this is what I cut it to for these different plots. Okay, so let's try to estimate that. And what we do is if we look at the minima of that curve as a function of bond dimension, we see these curves are almost horizontal, which is telling me that I don't really need to put a lot of bond dimension in the matrix product state to actually calculate this quantity because it's a macroscopic property. The other thing which many of you might have noticed is that for these system sizes, which are big enough but not huge, we do see some finite size effects in the few percent level, and I'll talk about that in a minute. But the important part is because these things don't seem to be sensitive to bond dimension, we can scale this up and try to study this phase transition in more detail. Okay, so now, but first, let's try to understand why is this working. So if I look at this quench dynamics, which I do completely classically and do the time evolution using matrix product states, and I pick a bond dimension 64 and 128, and I use the squared Hilbert-Schmidt distance defined like this, and I compare the different properties of the time evolved state. What I see is if I compare the full wave function, we see that initially the approximations are good because these two simulations agree with each other, but eventually they reach a value of the order 1, which is suggesting that these two states are almost orthogonal to each other. So this is telling me that I cannot really write down the wave function. It's impossible to write this down because the worst thing you can do to approximate a pure state is pick a pure state that's orthogonal to it. However, if I look at these local reduced density operators, and I also have site and time averaging because that's what goes into my order parameter, we see that these Hilbert-Schmidt distances are much smaller. They are of the order of 1 part in 10,000 or 1 part in a million. And this is why our different bond dimension simulations agree with each other on these order parameters, because these macroscopic properties are a lot less sensitive to the exact wave function than obviously the exact wave function. And why is this calculation difficult? Oh, by the way, this line is what you would get if you do the same thing for a random MPS. So this might just be a property of marginal states. So the reason our ability to calculate the full wave function is bad is because entanglement does grow as a function of time, and eventually this does reach volume law entanglement. In fact, I don't have the plot here, but we do see signatures of volume law entanglement even at these short lengths. And what you see here is if you pick a particular bond dimension, the amount of entanglement in the wave function is bounded above by the bond dimension of that simulation. And this is why our ability to calculate the wave function is bad, but we're still able to study the phase transition reasonably well. Okay, so I did say something about finite size effects, so I'll get back to that. So my order parameters are MZ and MZZ. And if I want to believe the traditional ideas of these kind of phase transitions, the phase transition is really studied in the thermodynamic limit where the system size goes to infinity and the steady state limit of the quench time going to infinity. Now, no matter which computer I use, I don't have enough memory, so I can't really take the thermodynamic limit. And we have deadlines. You kind of want to finish our project, so we can't really take the steady state limit either. So what we'll do is we'll just use a well-known idea of finite size scaling, look for a curve collapse, and look for universal behavior. And if we do this, we can, for example, consider a scaling to the thermodynamic limit. Now, when we do this, we implicitly assume that steady state has been reached. So I'll assume that my quench is infinitely long and have this scaling ansatz as a function of the system size by introducing these critical exponents. And I see that this enterprise is also successful and we are able to see this curve collapse. And we are also able to extract some of these critical exponents and critical point, which I'll say a few words about in a minute. But if I do the other way, where I implicitly assume that my system is big enough, I have reached the thermodynamic limit. But now I ask the question, how is the scaling with the quench time? So now I have some other critical exponents. And then I see that even in this case, even with the extremely low bond dimensions, our curve collapse is successful, allowing us to extrapolate, or I should say, extract some of these critical exponents. But I want to say a few words. All is not well. In particular, let's look at one particular instance of this finite size scaling. So now let's consider the first case, which I mentioned, where I assume that the system has reached steady state, and I look at the scaling with respect to the thermodynamic limit. And if I do that, I can ask the question, well, what time do I do this? So what we'll do is look at the estimate of the critical exponent nu as a function of the quench time, which really I'm assuming is infinity, but it's not really infinity. And this is the plot I have here, right? So this is the critical exponent nu as a function of how long the quench time is, which I'm calling infinity behind everyone's back. Right. So one thing I'll note is just as the theme we've had so far, that all of these critical exponents are basically the same, regardless of which bond dimension I'm using, above 16. In fact, there are multiple lines here. You can barely distinguish them. So maybe I don't really need to dial up my bond dimension. But all is not well here. If you notice, there is a temporal drift in this critical exponent nu as a function of time. Now, what does that even mean? What does it mean to have a critical exponent that changes with time for something where I should have reached steady state? Well, I interpret that as we haven't really steady state, and I was lying all along when I said implicitly the steady state has been reached. Maybe this is sensitive to MPS truncation, and maybe this is where we need a quantum computer, and no amount of MPS can actually do the job. So maybe this is what we should tell our trapped ion friends to build a quantum computer for in analog mode. Okay, so I just want to take a step back and think about efficient classical simulation. So when I talked about these order parameters, MZ and MZZ, they are macro properties insensitive to bond dimension for the reasons I mentioned, because they really depend on these local properties. So we have efficient classical simulation for them. We could also do curve collapse by extrapolating the thermodynamic and steady state limits. So we're able to get all of these things reasonably well. And there seems to be an efficient classical simulation. However, all is not well. We do have temporal drifts, and maybe this is where our classical methods break down, and we need a future analog quantum simulator. Okay, that's all I have. I want to acknowledge all the people I worked with during my PhD, including my advisor, Ivan Deutsch, at the University of New Mexico. We were also funded by the Quantum Systems Accelerator led out of Berkeley lab. And notice that I did not use NERSC, and that's because we didn't need to, because we could just run these programs on simple computers. I want to take a minute to acknowledge the first people of New Mexico and Oklahoma, and thank you for your attention.
Great talk. I'm wondering, have you tried the same on IP model with disordering? Would that make classical simulation more difficult or easier?
So have we tried it? Yes. Do we talk about it in our paper? No. But what we find is if you have a strong enough disorder, we reach a regime of many-body localization, which actually makes this much easier.
What about in terms of dynamic or phase transition?
Well, okay, so that's a great question. We don't necessarily have this dynamical phase transition because if you do have many body localization, we don't have this dynamical phase transition. So, and this is why I don't want to make too many claims about it because we have to fine tune to a regime where the dynamical phase transition exists and then study whether we can do that. So, in addition to a computational problem, it's also a parameter tuning problem. But that's an interesting follow-up work which we could do.
Yeah, I'm very curious. What about like, do you have any intuition like when there is disordering? Is there a case that will make classical simulation very difficult and the quantum simulation easy, like John Preskill?
So my guess is, and don't quote me on this, I may be completely wrong, and it'd be great if I can scroll through the archive and find someone proving me wrong, which is if the disorder is not strong enough that where we do break a lot of these symmetries, we should find something interesting. But if the disorder gets extremely strong, I shouldn't say extremely strong enough, we would have many body localization, which is actually very easy to do classically because we barely have any entanglement growth. But again, what is weak enough is something which I don't know and would be interesting to scroll through the archive to find out.